All right, so let's continue on from what we covered last week. So let's quickly review the material. So we talk about control dependence. We talk about how to handle if else or for loop. Because if you think about the computer being dumb, I mean, to be honest, everything that you're working on right now is like really dumb, and you are the smart person to control everything, right? To make sure they're doing something useful, and the computer are essentially doing something really, really, really quickly, so they become really useful for us. Essentially, it can only do top to bottom kind of execution. You go to the first line, then the second line, the third line, then the fourth line, the fifth line. But then in your case, right, we're gonna have control dependence or something we call control dependence because sometimes we need to check a condition. If this is true, do this. If this is false, do something else. Or something like a loop where we repeatedly do something until some certain condition happen. You do the summation for the first 15 numbers, so you're going to loop around for 15 times, right? How do we control? How do we build? Basically, we're building a computer. So how do we build a computer such that they can handle condition, right? Um, so we said about branches, we have the ISA command that allow you to branch things. But the thing is, with pipelining and with data forwarding, when we have to have branching, it basically means you're stalling the pipeline, right? So the question is, are there better options than stalling the pipeline, right? So we also talk about the information we need to be able to do a good job at handling control dependence, right? So the first question is, for every single instruction we fetch, right, we need to figure out, is that a branch? Because if we don't know if that's a branch or not, we don't know what to do, what to fetch next, right? Essentially, if you don't know if that's a branch, you don't even say, hey, can I fetch or can I not fetch? Then the second thing is you need to find the target address, which is um, uh, where are we jumping to, right? Are we jumping to this beginning of the if or the else, or if you have a switch case, where do we jump to? If you have a jump table, how do you predict the target address, right? Then we said, hey, the branch target buffer can be used to do both things, where it think of it as a set, right? If you have a target address in this set, it means the instruction is a branch, and you use the program counter as a key to search the set. And to implement this in hardware, we can use a giant table and say, hey, if you use the program counter to search into the table, there are more tricks to how to index into the table. We can cover a little bit more detail on this when we talk about caching, right? Because the technique are similar. But anyway, so the overall idea is, let's have a giant table, use the program counter as a key. If you search the table and you cannot find the key, it means the instruction is not a branch, so you go to the next instruction. If you use the key and search the table and you found the target address, it means that, hey, maybe that's it's a branch, right? That instruction is a branch. Then you have another smaller table to predict. Well, it's an if else. Are we jumping? Are we staying where we are and go to the next line? So that's a direction predictor, which comes to the next issue, right? The remaining question is, if this is a branch instruction, are we going there or are we staying on track and move to the next line, right? And we talk about the branch prediction. We talk about the last time predictor and 2-bit counter, and we kind of go over, right, quite a bit in detail, the 2-level prediction, right? So for the 2-level prediction, we can kind of improve by using these two observations. When you have branch in your code, right? Basically, what happened earlier is going to impact what happened later. That's the nature of life, right? To be honest. But we can use the same observation and say, hey, if this if else is true, maybe the next if else can be impacted by the earlier condition. So we call this a global branch correlation. There are correlation between each branches in a global level. I mean, some branches are independent from each other for sure, right? There are going to be cases, and you'll see in the sample exam that I'll put it on the class website. that you can check out. I mean, there are branches that has no global correlation, and there are branches with some global correlation. Then again, within the same branch, there are certain part of the branch. I mean, to be honest, when you loop around, for example, right, what happened earlier might impact your own branch. So that's a local branch correlation. And based on that, we have the 2-level predictor that we practiced last week, right? Now let's talk about, do we have any other techniques to handle branching, right? And the answer is yes, right? So there are more things you can do from your lab, right? From your lab. One of the techniques you are going to see in the MIPS processor is called delay branching, or the branch delay slot, right? So the way it works is, well, when I see a branch instruction, all right, whenever I see a branch instruction, again, I have fetch, right? My pipeline, I have fetch, decode, execute, memory, and write back, all right? And here's the thing. Over here at point A, I know this is a branch, right? I know this is, all right, I cannot write English, sorry. I know that the instruction is a branch during the decode stage. The problem is, I do not know the condition until B. Know the condition of my branch. I mean, know the outcome, to be honest, right? You know the outcome. Are we going to the if, or are we going to the else? The condition check, if A is less than B, if A is equal to B, that's done during the execute stage, right? So the observation of the branch delay slot technique is essentially, well, if you're gonna just have to wait one more cycle, right, to know your condition, why can't we just now crawl through your code and then see if there's any instruction we can do in the middle that has nothing to do at all with your branch. And you must execute instruction anyway and put it there. So again, the technique, it revolves around, we're gonna delay your execute stage until we know, right? Until we know the condition of your branch. And then for the next instruction that come afterward that you're supposed to stall, right? Because I mean, you have to keep the branch instruction going into the pipeline. You insert the bubble because you don't know what to do. That bubble will fill with instruction that has nothing to do with the branch at all. เดี๋ยวขออธิบายภาษาไทยนะครับเทคนิคนี้มันไม่ได้มีอะไรมากก็คือว่าถามอีกทีนะสำหรับน้องๆทุกคนเรารู้ว่า instruction นี้มันเป็น branch เมื่อไหร่ตอน decode พอ decode ปั๊บเรารู้ว่าอันนี้ branch แต่ว่าเราไม่รู้ว่ามัน branch แบบต้องกระโดดไปหรือเปล่าหรือมันจะไปบรรทัดต่อไปจนกว่า execute ใช่ไหมเพราะฉะนั้นมันจะมี delay หนึ่ง instruction ไอเดียของ branch delay slot เนี่ยก็คือว่าก็เราต้อง delay 1 instruction ใช่ไหมครับเราก็ให้ compiler วิ่งไปดูในอนาคตเลยโค้ดเราในอนาคตเลยแล้วดูว่ามีบรรทัดไหนไหมที่สามารถรันได้เลยตอนเนี้ยแล้วมันก็จะเอาบรรทัดนั้นอะมาเสียบไปตรงนั้นเสียบไว้เพื่ออะไรที่แทนที่เราจะต้อง delay ค่ะมันก็จะไป fetch instruction อันต่อไปแทนที่มันไม่เกี่ยวอะไรเลยกับ branch อันนี้คือถึงแม้มันจะต้อง take branch หรือมันไม่ take branch มันรู้ว่าอันนี้มัน independent กับ condition ของ branch เลยก็ใส่เข้าไปได้นะครับมีคำถามไหมครับ So the next question is, well, the branch delay slot sounds nice, right? We're gonna go in the future and find independent instruction that can execute right away. Here's the magic. How do we do this? Well, we handle the magic with compiler, right? To be honest, you basically have to go search in the future and see if there's any possible instruction that you can slot in, right? In the hardware, you don't have to do anything. You just keep delaying. Basically, in the decode, you see it's a branch. You don't have to put in the bubble. You keep going, right? And then your assumption is the next line you can execute. If you cannot, the compiler would insert no op, no instruction. I cannot find any future instruction to slot in, right? And that's okay. So that's the delay slot, right? And for unconditional branch, the one that you always have to jump in, that's easy to fill in because you know that you're gonna jump there in the first place, right? So you can find anything from the location you're jumping, fill it in the slot. For conditional branch, this is harder. Why is that the case? Let's say this is your code, right? You have a branch. If true, you do this. If false, you do this. So that's a conditional branch. You check true and false, right? And let's say this is a huge block of code, right? That do a lot of things and you merge back after you're done, right? If else, and both if else are really long set of code, right? And then when you're done, you're merging back. Basically, this is called merging, right? At the time you're merging, there's no independent instruction because everything you do afterward depends on something in the branch, right? So it might be the case where you cannot find, right? Cannot not find independent instruction because the if and else are doing a lot of things and everything you do depend on something in the if else. All right. So that can be harder. In that case, you fill in with no ops. Well, I give up. I cannot do anything. Just stall. Right? So here's an example. So let's say I have a code that do add, but let's say I do an add, R0, R1, R2, and then you do branch if not equal, right? So basically you branch to a target, right? If R0 is not equal to 6. So if R0 is not 0, you branch, right? Then let's say that in a normal code, or this is a normal code, and over here, this is a delay slot with delay slot, right? And over here, you do a subtract, 0, 1, 2. Then you have a target here, right? And then you add 2, 3, 4. Then over here, right, afterward, you fit, like you keep continuing execution, you do maybe subtract 8, R9, and R10. So you notice that this subtract has nothing to do with whatever you do during the branch. If you're taking the branch, you jump to target, you modify what? You're going to modify R2, right? You add R3 and R4, write the result back to R2. Well, it's okay. R2 is modified. I don't need it. My subtract only need R9 and R10. So yeah. The condition of your branch depend on R0. R0 is the result from the previous add, right? So you need to kind of check if R0 is 0 or not. Even with the data forwarding, you still need to do the comparison between R0 and 0. Then the subtract afterwards going to modify R0. Again, it's not modify anything from R9 and R10. So I can definitely, right? I can definitely slot in the subtract. So over here with the delay slot, right? You do the add, you then do branch not equal, right? The branch not equal R0. Then right after branch, you do the subtract. R8, R9, and R10. Then you continue with the this one, the subtract R0, R1, and R2. Then you do the add, R2, R3, and then R4, and then the rest of the code continue the same way, right? So you will see, here's how it works, and the target is here. Right? You will see what actually happening here is this adds go to here, the branch not equal here the same order, but your subtract is now going here, and this is basically what we call the delay slot. by the time the subtract is in the pipeline, you move the branch not equal to the execute stage. So now you know for sure whether you have to jump to target or not, right? Then you can update the program counter accordingly. So in this case, the subtract that move here, the add that move here, it's okay. I mean, I will now know whether I have to jump to target or not, or just move to the next line. Again, let's do this in Thai again ก็คืออันเนี้ยเราจะหา instruction ข้างหน้าในอนาคตมาเสียบเข้าไปหลัง branch เพราะเรารู้ว่าหลัง branch 1 instruction อ่ะมันจะต้องรอให้มันเสร็จให้มันวิ่งเข้าไปใน execute stage แล้วมันดู condition ว่าอย่างอันเนี้ย r 0มันเท่ากับ0หรือเปล่าถ้ามันเท่ากันปั๊บบอกว่าโอเค condition ตรงเพราะฉะนั้นมัน branch not equal เนาะเพราะมันไม่พอมันเท่ากับ0มันก็จะต้องวิ่งไปบรรทัดต่อไปถ้ามันไม่เท่ากับ0มันต้องวิ่งไปที่ target ซึ่งณตอนนั้นน่ะเรารู้แล้วเพราะฉะนั้นการที่เราดีเลย์ไป1 สล็อตแล้วไอ้สล็อตที่เราดีเลย์เรานั่งทำอะไรที่มันไม่เกี่ยวอ่ะแต่ว่าเราต้องทำอยู่แล้วในโค้ดอ่ะเราก็ไม่ต้อง stall pipeline เพราะฉะนั้น pipeline ก็จะ full so basically after this delay slot your pipeline is fully occupied right so I mean you can have a fancy version of delay slot where you can do squashing right so let's say the branch instruction has to fall through means you keep doing here for example right you have instruction A B and then you have branch X branch to X basically branch back you see it's branch back to instruction A and B so basically what you do is A B and you will take the branch you do A B again and you take the branch again A B again think of it as a loop think of this as a loop you do A B A B A B A B until some condition becomes true and you go to the next line D and E so that's a normal code right so with delay slot right with delay slot over here right you do A B and then you branch and then let's say you cannot do anything to figure out okay are we have any independent structure so we cannot do that let's say we cannot find any independent structure so we put in no op branch X we do nothing if it's true go back to A and B X no op A and B X no op right then you after branch condition becomes true you would then put in instruction D and E right so that's a normal delay slot and if you cannot really find anything else well too bad you cannot fill in the delay slot right now with squashing basically means that if I don't have to do this if I notice this is the wrong path I get rid of it right so that's squashing so what you have to do now if you can squash is because it's a loop but most of the time you're going to go back to A right I mean that's the nature of a loop you're going to repeatedly doing the loop for most of the case and if you only exit at the end so it's actually a smart decision to guess right this is almost like a branch predictor but you guess that well it's a loop so you're going to do instruction A anyway so you would do A B and then branch X A right but because you're doing A, you jump back to B. So basically, it's going to be A, B, A, B, A, B, A, B, but instruction A is being slotted in during the delay slot. But then, with squashing means that if the last case where you have to follow through, when you're done, right? When you're done exiting the loop, you know that you're not doing A is in the pipeline. In this case, branch X is in the execute, instruction A is in decode stage. But condition is wrong, so you get rid of A. A is gone. It's not being committed because it hasn't finished the write back. So that's okay too. So the only difference here is with squashing, you eagerly, right? You aggressively put A in the pipeline. Then, if you don't have to do A, you throw them away and you keep doing the rest. Right? And that's it. So that's how delay slot with the squashing works. All right. Now, the next technique is something that is kind of like being used aggressively by the GPU, right? So what we can do is when you have anything to delay your code, you can do something else, right? So one thing you can do is we can use a technique called fine-grained multi-threading. And we kind of dig deeper into how this works later when we talk about the GPU. But one of the technique you can do is you maintain a lot of hardware threads. Hardware threads means that you are going to maintain the context for each thread that you're running. And then for each cycle that you're supposed to delay, you don't know what's the outcome of your branch. You run a different thread. So this allows you to keep context switching in hardware, because context switching in hardware is really good for, well, in terms of performance, it's really good. It's just so costly to maintain all these active threads, right? But when you resolve the branch, by the time you know the condition, well, you haven't fetched the same thread again. So essentially you keep fetching the new thread. So the downside of fine-grained multi-threading is gonna have a low single thread performance. And you need extra logic to keep thread context, right? So here is the idea, right? I will draw what happened in a bit. But let's say you can write a parallel program. So it's a program A, right? That can spawn multiple thread. Thread 1, thread 2, thread 3, thread 4, thread 5, and all of these 5 threads can run in parallel. So let's assume all these 5 threads can run in parallel. All right. And you know that you have to fetch, decode, execute, memory, and write back, right? So during your execution, what's going to happen is you do thread 1 fetch right here. In the next cycle, thread 1 fetch go to here. Then you feed in thread 2 fetch. In the next cycle, thread 1 decode go to execute. You move thread 2 from fetch to decode. You feed in thread 3. Then you move thread 1 here, thread 2 here, thread 3 here, thread 4 here. Then thread 1 is here, thread 2 is going to be here, thread 3 is going to be here, thread 4 is going to be here, right? And thread 5 is going to be here. So that's the first instruction for each of the 5 threads, right? You can finish everything. You don't have to even do data forwarding. You don't need anything because you haven't even fetched the second instruction in the first thread yet. Over here, we are fetching the first instruction for all the 5 threads. And by the time thread 1 finish write back, now you can do thread 1, instruction 2. So this is thread 1, instruction 1. Thread 2, instruction 1. Thread 3, instruction 1. Thread 4, instruction 1. Thread 5, instruction 1. Now that thread 1 is out of the write back stage, there's no dependency at all, so we can fetch the next instruction, right? This is basically the main method at how GPU run your code. It doesn't have any data forwarding logic, to be honest, right? Fundamentally, you just keep context switching until you're out of the pipeline, then you fetch the new thread. If you will, you can do some data forwarding, but this eliminates control flow and eliminate a lot of data dependency, right? What's the overhead here? You need to write a program. That's a bummer, because if you have so it has to be a parallel program, but each of the thread has no dependency as well, right? Because you need to keep feeding in all these threads. So that's how fine-grained multi-threading works. It can be really, really, really fast for your program performance, but for the single thread performance, this is going to be really slow, because thread 1, each instruction would take 5 cycles. So the instruction throughput for each of the thread would drop. But for your program, it might go up because you're running multiple threads in parallel. This is like a power parallel programming. All right. It's being proposed, being used a while ago, actually. To be honest, it's kind of being used in the CDC 6600 in 1964, right? This is one of the earlier machine that used fine-grained multi-threading. Then the Core HEP, another machine, also show how you can do a MIMD machine. So this is multiple instruction, multiple data. In the 1978, the paper is published during the time, right? So these are a classic old idea that works really well. Then the GPU, like company like NVIDIA, and back in the day the ATI, right? What now becomes the GPU wing of the AMD. Kind of pick up this idea and use this aggressively originally for their graphic workload, for gaming, for rendering, but now we use it for everything in the GPU application. Okay, so example is just the one I showed earlier. Now, the next thing that we have to cover is, well, we can also get rid of control flow through predicated execution. Predicated execution, if you have worked using assembly code before, you might see this before. These are sometimes we call condition code. It's the instruction that only, right, only execute if certain condition register is true. So the idea is we would convert control dependence into data dependence. One example is used aggressively in the ARM ISA. I can use the condition register to check what should be executed. And you execute the instruction only if the condition becomes true. Otherwise, you don't run that instruction. So it means that the condition becomes data dependency, right? Which means you can do data forwarding. This eliminates branching because you always have to do that instruction regardless. As in, like, you always have to fetch and decode that instruction regardless. If you do not have to execute instruction, it's fine, right? But this allows you to do data forwarding. So the benefit is this get rid of hard to predict branches, and you can actually do a lot of code optimization and allow like a creation of a much bigger basic block for the compiler. So if you study compiler, if you study code optimization through the compiler, you know that the basic block, the size of your basic block matter. It allows you to move instruction within the basic block to optimize your code easier. The downside is, well, if branches are easy to predict, if your branches are all easy to predict, it's going to cost useless work because by this time, I just told you, right? I have to fetch and decode, and then you realize, oh, I do not have to run this instruction. So you throw it away. That's useless work. So if you do this too aggressively, you're going to run into the case where you do a lot of useless instruction that not supposed to be run. And you also required additional hardware and ISA support for predication. All right, so that's all for how to handle branching. Now we are moving into the next concept called superscalar, right? So the idea with multi-cycle, so let me keep going forward because it's already been only half an hour. So the issue with multi-cycle execution is sometimes instruction take a different amount of time. For example, right, an adder would take less time to finish than a multiply. Just because multiply consists of a bunch of adding, add, shift, add, shift, add, shift, right? That's how we do multiply when you were in elementary school, right? So here's the issue. We need to maintain sequential order, and this is one of the most important things when you run your program. If you run your program, the programmer expects that the code gets executed in the order. เดี๋ยวขอแปลไทยนิดนึง so I'll explain this in Thai a little bit because this is really important เวลาเรารันโปรแกรมอะครับเวลาเราเขียนโปรแกรมก็ได้แล้วเราจะต้องตีต่างกันเลยว่าไอ้คอมพิวเตอร์ที่เรารันอยู่อะมันต้องรันตั้งแต่บรรทัดแรกไปบรรทัดที่2ไปบรรทัดที่3 4 5 6 7 8จนบรรทัดสุดท้ายอันนั้นคือ assumption ของมนุษย์อันนั้นคือ assumption ของโปรแกรมเมอร์เพราะว่ามันอยู่ดีมันรันบรรทัดแรก2 3แล้วมันไปรันบรรทัดที่10 11 12เนี่ยแล้วกลับมารันบรรทัดที่4 5 6ไม่ได้โดยเฉพาะถ้าจะดีบักโค้ดเนี่ยไม่ได้เราไม่สามารถเข้าใจได้ว่าทำไมอยู่ดีคอมมันไปทำออเดอร์นั้นคอมมันต้องทำออเดอร์แบบบรรทัดที่1 2 3 4 5 6 7 8 9 10นะครับอันเนี้ยเขาเรียกว่าการ maintain sequential order so your computer must from the programmer point of view must maintain sequential order All right. But let's say I have this. I have the add instruction followed by multiply, right? And then another add come after it. The thing is, the multiply can block the progress, right? And the ISA still demands sequential semantic, basically the in order instruction processing, right? If you try to like sneak in the future instruction and then there's some bug like segmentation fault or something that crash your program, the program will be like, why is it executing this instruction in the future, right? So superscalar architecture, basically a quick revisit to the idea is essentially, right? One thing we can do is during the write back, I'll guarantee the write back happen in order. But I'll aggressively fetch the instruction into my pipeline, right? These allow, for example, let's say you design your ALU, right? It's your ALU. You have adder, and you have to multiply, right? Let's say I know the multiply takes a long time, but we do multiplication all the time. So to save time, we buy 2 units of the multiplier and 1 unit of the adder. So in this way, if I need to do 2 multiply, I'll do the first multiply in the first unit, second multiply in the second unit. I can do that, right? And what I guarantee is in my pipeline, right? Fetch, decode, execute, memory, and write back. You are kind of guaranteed that this is when the programmer see the change. The programmer doesn't see what happened during the fetch, decode, execute, and memory, and it's not exposed to the programmer. So I don't see what happened in the middle. So as long as I can maintain the order, the sequential order in the write back, I'm good. All right. So again, let's do this in Thai. ก็คือถ้าเรารันโปรแกรมใช่ไหมแล้วเราบอกโปรแกรมเมอร์ไม่เห็นหรอกว่าใน pipeline เกิดอะไรขึ้นบ้างแต่เรารู้แค่ว่าหลังจากเสร็จ write back อ่ะพอเราเสร็จ write back ปั๊บอันนั้นคือจนตอนที่โปรแกรมเมอร์เห็นการเปลี่ยนแปลงจาก instruction ของเราคือ instruction เรามันจะไม่เสร็จสิ้นจน write back เสร็จเพราะฉะนั้นอ่ะเราก็แค่ต้องเรียง instruction กลับมาใหม่ตอน write back คือไอเดียคร่าวๆคืองั้นเราก็แค่การันตีว่าเราต้องเรียง instruction กลับมาให้เหมือนเดิม1 2 3 4 5 6 7 8 9 10ตอน write backแล้วถ้าสมมุติเรามี multiply 2 ตัวเงี้ยกับ add เราก็ใส่ add instruction sneak เข้าไปเลยปุ๊บแล้วค่อยเรียงตอน write back คือสมมุติไอ้ add instruction มันทำได้เลยแล้วมันไม่ต้องรอ multiply ก่อนหน้ามี multiply ตรงนี้สมมติ instruction เรามันเป็นแบบ multiply add แล้วไอ้ add ตัวนี้มันไม่ได้ depend on multiply แต่ว่าถ้าตามจริงอ่ะเราควรจะต้อง run multiply ให้เสร็จ run multiply อันที่ 2ให้เสร็จแล้วค่อย run add อันที่ 3เราบอกว่าก็ adder มันฟรีว่ะมันไม่มีใครใช้อ่ะเราก็ fetch มาก่อนเลยก็คือ super scalar architecture คือเราจะ fetch ทุก cycle fetch ไปเรื่อย fetch แล้วเอา instruction ที่เรามีอยู่อ่ะแต่ยังไม่ได้พร้อมที่จะ run บางอันมาตั้งกองไว้แล้วเราก็ดูว่าเรา run อะไรได้บ้างอย่างอันนี้สมมุติกรณีที่เราตีต่างของเรา run add ได้ก็เสียบเข้าไปเลยใน execute unit แล้วเสร็จแล้วเราไอ instruction ที่เราตั้งกองไว้อ่ะเราก็เก็บออเดอร์ไว้ว่าอันนี้คือ instruction ที่ 1 2 3 4 5แล้วเราการันตีว่าตอน write back อ่ะมันต้อง commit การ write back ตามออเดอร์เดิมก็คือ 1 2 3 4 5นะครับ so basically the superscalar architecture guarantee that the write back is done sequentially in the pipeline you can do whatever as long as we do not modify the architecture register we modify the register file in order based on instruction sequence. Whatever happened in the middle, we don't care. By we don't care, we can optimize as much as we can, right? And again, in this case, instructions start to execute out of order. In the pipeline structure, instruction 1 can be in the execute while instruction 2 is in the memory, right? Instruction 1 in execute stage, instruction 2 in the memory stage. So your pipeline can look like this. So this is your pipeline, right? fetch, decode, execute, memory, and write back. So instruction 1 can be here, instruction 2 can be here, instruction 1, maybe it's a multiply, so it takes a long time. Instruction 2 beat instruction 1 is now in the memory stage, right? Instruction 3 is here, instruction 4 is here. Once this happens, as long as you guarantee that the programmer will see update in the register file in the sequence of instruction 1, 2, 3, and 4, we are good. All right, so here's the requirement. How to enable this, because this is definitely faster than a normal in-order pipeline. So to do this, one thing, we need a huge buffer to keep fetching. We're going to keep fetching instruction into this pool where we can then figure out who can go, right? So the first thing is we can add this thing called instruction window. Instruction window is a buffer that stores fetch instruction. So we keep fetch, the fetch unit keep going, fetch, 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 and then it fetch to instruction window. Then the decoder say, okay, I'll look at this instruction window, look at this huge buffer and see who can be dispatched. So the decoder's job now include how do I dispatch things. Then the process is going to have a bunch of ALU. It might have 4 floating point unit, 3 multiply, 2 add, 2 adders, right? So in that way, you can do like 2 add, 3 multiply, and 4 floating point operation at the same time. Whenever these units are free, you dispatch the instructions that are not dependent on anything earlier. Anything you can do forwarding is also okay, right? You dispatch them to the ALU. Now, the instruction, right, it's gonna be issued in the data flow order, and now it's gonna be data flow order because I do out of order instruction dispatch, right? Whenever ALU is available, I start to run whatever is ready. That becomes the data flow model. Now, to guarantee one Neumann model, which is sequential instruction processing, I finish the first, second line, third line. I finish write backs. We call this retiring the instruction. So we finish the write back in the same order. It's like in the write back stage, we sort everything back to instruction 1, 2, 3, 4, 5, and then we retire based on the same order as coming in. So the superscalar architecture basically is how we'll have the fetch that keep feeding new instruction into my instruction window. The instruction window will hold instruction you're fetching. So it can be instruction 1, instruction 2, instruction 3, instruction 4. And it's going to keep fetching until this thing is full, right? Then in the decode, it performs this dispatch, where it figure out this is your ALU, right? It's going to be an adder, multiplier, and maybe like a floating point unit, right? Then you dispatch the instruction to these units based on whether they're ready or not, right? So let's say instruction 2 is not ready. It stayed there in the instruction window. It allows instruction 1, 3, and 4 to go in. And then instruction 2 can go in afterward, and that's okay, right? And then you finish the memory stage, and in the write back, right? You then basically sort things back in order. You basically just now need to commit the modification to the register file in the order of instruction 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That way the programmer doesn't feel things are weird. But in the hardware, we are doing things out of order to make it faster. All right. Let's take a quick 10 minutes break and we'll come back at 10 o'clock. Then we'll talk about precise exception. All right. This is basically the latter half to the lecture. As I told you, we might be done with this lecture sooner to be honest, because I just want to make sure we wrap up precise exception and the structure to support precise exception. Then we go into a much more detail with an actual example with out of order scheduling next week, because that requires more than 1 hour. I cannot fit into that last hour. All right. So let's do a quick break. We'll be back at 10 o'clock.